All right, number 16. 10.3, number 16. Here we go. That would be easier to do if I had the sheet. No, that's honors. Here we go. Yes. Okay, so let me do this. Let me steal the figure from the worksheet. Okay, so here's our figure to work with. So what does it tell us? In the figure, block 2 has a mass of 1 kilogram. So this guy's 1 kilogram. It's moving... Oh, I'm reading the wrong problem. Man. All right, let's see. In the figure, block 2 has a mass of 1 kilogram. Is that what I just said 2 seconds ago? Wow, what's going on with me? All right, block 2 has a mass of 1 kilograms. It's at rest. So the velocity of block 2 initially is 0. This is the mass of block 2. Your notation here is super important. It's at rest on a frictionless surface and touching the end of an unstretched spring. So that means our x initially is 0. I guess I should say, yeah, whatever, that's fine. We know our spring constant is 200 newtons per meter. What else do we know? The other end of the fixed spring is attached to a wall. Cool. Block 1 has a mass of 2 kilograms. That's confusing. Mass 1 is 2 and mass 2 is 1. Thanks, stupid problem writers. All right, so it's traveling at a speed of 4 meters a second. So the velocity of block 1 initially is 4 meters a second. It collides with block 2. The two blocks stick together. When the blocks momentarily stop, by what distance is the spring compressed? This is a great problem. Okay? Like, this is like totally, I could see this being an AP style problem. The only difference is they would probably call this M and this 2M. But otherwise, this is right on for AP level difficulty. Okay? So what we're trying to figure out is what? How far the spring gets compressed when they stop. So, thoughts? Sure, get me started, Toby.
Something about force and integral. Not an integral. Force. You have to find force.
So talk to me about what's leading you in that direction? The spring constant?
Oh, yeah, and the fact that force equals kx, so you're going to need to find that value to solve for how far you're going to go.
Okay, so important tangent. Force of spring is negative kx, right? If you integrate this, you get negative 1/2 kx squared. The work that the spring does is equal to the opposite of the change in elastic potential energy. Okay? So I see people do this all the time with springs. Okay? Again, only use calculus if you absolutely have to. Okay? If your acceleration isn't constant. Okay? Here, our acceleration isn't constant, but we already know an expression for the work done by a spring, or equivalently, the change in elastic potential energy. Okay, do you see what I'm saying, Sebo? So, yes, force is important here because the two objects are exerting forces on each other, and the spring is going to then exert a force on the combined system. But I guess I don't see how that gets us a path to the solution. Do you know what I mean?
Yeah.
A little bit? Okay. Sure. Heidi, what do you got?
Well, I found the kinetic energy initially, which was...
Okay, so the kinetic energy of block 1? Okay, cool. So that's whatever 1/2 mv squared, so you're going to get, what, 8? 16. Okay, sorry.
And then I found what would be the final kinetic energy if they collided without the spring,
Okay.
which was 10.67 joules. I can't really remember how I got that, but I got it. And I set it equal to the amount of elastic potential energy that the spring,
You set what equal to the elastic potential energy?
the final kinetic energy.
Okay, so did you actually use the 16?
Yeah,
Or-
I assume that's how I got the final kinetic energy.
Gotcha. Okay. All right, you're in the ballpark. So you're good to be thinking about energy. So let's consider the energy for a minute, all right? So I don't want a solution right now. Let's think about what's going to happen with the energy, okay? So I think you're right to be doing that because at the point when the system stops, where's all of my energy? It's all elastic potential energy, right? Okay? Now, there are two other energies that we need to consider, and Maggie's done exactly that. There's kinetic energy before the collision and kinetic energy after the collision, right? Like, right before the collision, block 1 is moving, and right after the collision, both blocks are moving, right? Because they just collided, right? So, should those kinetic energies be equal? Should the kinetic energy before the collision equal the kinetic energy after the collision?
No.
No. Why not?
Different velocity. It's a collision mass. It's a completely inelastic collision.
Oh, there you go. Completely inelastic collision. Okay, remember, the only time that your energy would be conserved in a collision is if it was an elastic collision, and it's not. They're sticking together, so you're going to lose kinetic energy. Okay? My only concern is I guess I'm not sure how you used that initial kinetic energy to find the final kinetic
Maybe I
energy.
just found it and didn't do it.
Yeah, because I don't think it helps us any. So we got to find a way to deal with this. Idea question, Sarah, or a question?
Question. How do you know it's completely inelastic?
Oh, really good question. Somebody help out with that. How do we know that? It's got to be completely inelastic because the text of the problem tells you they stick together. Let's see. Traveling at speed 4 meters a second collides with block 2, and the two blocks stick together. So that's the definition of a completely inelastic
What is this?
collision. 16?
Okay.
Oh, okay. McKeever?
So, why is the kinetic energy of, okay, so if you find the kinetic energy of the system before the collision, it's the same as the kinetic energy after the collision, which
No,
confuses me.
it's not. That's what we were just talking
No,
about.
but if you find it of the system, like if you find the center of mass and you find its velocity, and find the kinetic energy from the center of mass, it's equal to the kinetic energy of the block then after the collision. I don't know why.
I don't think you can talk about the kinetic energy of the center of mass. Well, if you're telling me that the kinetic energy before and after the collision are equal, then it doesn't work because they're not
The
equal.
kinetic energy of the center of mass is the same before and after the collision.
Well, no, think about it. It would be 0 at one point, right? Like the second they collide, it just
No, I mean before and after the collision, not before and after they reach the end of the spring.
Okay. Let me think about that. That doesn't sit well with me. Let me think about why. Okay. All right. So look. So the fact that we're trying to find the point where the spring compresses should lead you in the direction of energy. We're trying to find the point where your kinetic energy is 0 and your elastic potential energy is maximized. All right. The fact that there's a collision should lead us to think about momentum. Those are the two things we need to use to solve this problem. All right. There's a collision, so there's got to be momentum. The spring is getting squished, so there's got to be energy. Okay? So, let's analyze the collision. All right? So for the collision part of the problem, here's what I know. The total momentum before the blocks collide has got to equal the total momentum after the blocks collide. So that means the mass of block 1, I don't need to write out the big long equation, do I? All right, so let's see. So the total momentum before the collision is going to be 2 times 4, right? 2 kilograms times 4 meters a second, yes? Plus 0, right?
That'll equal 3.
So that's got to equal, after the collision, both of the blocks are going to be moving at some velocity. Let's call it v, just, right? Follow? I'm going to call it VF because otherwise I'm going to get weirded out by something later on. Okay, so that's VF. So both blocks have a mass or a velocity of VF. So I have 2 kilograms times VF plus 1 kilogram times VF, which, Sebo, to your point, is the same as 3 times VF. Everybody good? All right, so solve this, and you get 8 divided by 3, which is 2.6. So our final velocity is 2.6 meters a second. Now, what does that number mean? Like, what does it represent? The velocity of the 2 blocks after they stuck together immediately after the collision, but before the spring has been squished at all. Cool? Does this make sense? All right. So now it's just a conservation of energy problem, right? Now I've got this 3 kilogram block system moving at 2.6 meters a second. Okay? So now, for the spring squish, technical terms here, for the spring squish, the idea is the kinetic energy we've got before we squish the spring has got to equal the elastic potential energy we have after we squish the spring. Does that make sense?
Yes.
Okay, so kinetic energy before the spring gets squished is 1/2. My mass is 3 kilograms, right? The velocity we just found, 2.6 meters a second. Don't forget to square it. So 1.5, I don't know. Sarah, Maggie, is this what? Does that give you what you got? 10 point, whatever you said?
Yes.
10.6, cool. All right, equals 1/2 K, which was it 200? Newtons per meter times x squared, and solve for x. What just happened there? Did I steal your pen? I know, sorry. Well, it comes around, goes around, dude. All right.
That's great because you're missing 3 of your markers.
Say that again.
That's great because you're missing 3 of your pens.
Oh, right, yeah. Well, I'm holding 2 of them. All right. The green one's around somewhere. Okay, so does this make sense? All right, so I guess I'm trying to get better about making sure you guys understand how you know which problem-solving strategy to use. Okay? Collision or explosion, you should go, oh, momentum. Okay? Something squishing a moving thing colliding with a spring, you should think, oh, it's got kinetic energy, but the spring converts that to elastic potential energy. Okay? Good? Yes. 17 is very similar, if I recall correctly. Good? All right. As is 15, for that matter, I think. There's a few of those in here. All right. Good. Questions? All right. Awesome. Yeah. Oh.